We're going to talk about equilibrium. Now, of course, this is not chapter 15, it's actually 18. Sorry about that. Now, some reactions are going to go to completion. That means that all the reactants get used up and they turn into products. So like here, HCl completely ionizes into hydrogen ion and chlorine ion. We use a one-way arrow for these reactions, and this is what you guys have seen mostly. Most reactions, however, do not go to completion. All the reactants don't get used up. So what happens is the system reaches this dynamic state. Dynamic means moving, where the reactants are turning into products and products are turning back into reactants. So we use a two-way arrow for these types of reactions. So here, the N2O4 is changing into NO2 at the same time as NO2 changing back into NO2 or into O4. This is called chemical equilibrium. So this is the point at which the concentrations of all the species are constant. All right, so this is a dynamic equilibrium. The reaction doesn't stop. The rates are equal, meaning the forward reaction is happening at the same rate, the same speed as the reverse reaction. This happens in a closed system. In other words, there can be no outside interference going on. So a forward reaction looks like this, A going to B. We write a rate constant and it looks like this. Now don't worry about the rate constants. A reverse reaction would be where B goes into A. So notice that the rates are equal. So as A decreases to a constant, B is going to increase from 0 to a constant. And when A and B are constant, equilibrium is achieved. Now remember that the brackets here mean concentration, molarity. So let's look at two graphs here. Here's where your concentration of each one becomes constant. Notice they're not the same, but they are staying the same. The second is where the rates become the same. So this is the speed of the reaction. So both reactions are happening at the same speed. So forward and reverse reactions are going to continue to take place. The rate of the forward is going to equal the rate of the reverse. The concentrations are going to remain constant, but usually not equal. And just remember that equilibrium can only happen in a closed system. Let's talk about KEQ, the equilibrium constant. If this is our balanced equation, all right, we have our little coefficients here and we have our compounds here. So what you do is you put your products in brackets and you raise them to the power of the coefficients. And you put that over the reactants, also raised to the power of the coefficient. Now we're going to use KEQ here. There's specifically KC and KP depending on what you're dealing with, but for our course we're just going to use KEQ every time we see this, and it's a capital K. Alright, so remember that you put products over reactants. So if we're going to write the equilibrium expression for this particular equation, remember that our products are over here on the right. So this guy's going to go on the top, and we're going to raise it to the 2. All right, so we're going to square it basically and put that over our N2 times our O2. All right, so product raised to the 2, because that's its coefficient, N2 times O2. Now we leave solids out of our equilibrium expression because the concentration of a solid is not going to change because they have the same density. So if we see an equation that has solids in it, like NiO is a solid and nickel is a solid, we just completely leave those out. So we would have CO2 over CO. We also leave liquids out of the equilibrium expression because adding or taking away small amounts is not going to affect the overall concentration. So in this equation we have aqueous, we have gas, we have liquid. So we're going to leave out the water. Alright, so we have Cl2 raised to the 2 over our HCl raised to the 4, that's its coefficient, times O2. So only include aqueous and gas in your equilibrium expression. Now when you're writing an equilibrium expression, just a quick review, include aqueous and gas, do not include solids and liquids. Now KEQ is going to be based on molarities, the concentration at equilibrium. We don't put units on there. Remember that it's always products over reactants, and it doesn't matter how your reaction starts, you're going to reach that same equilibrium no matter what. So let's talk about the magnitude of the K value. If the K is a larger value, there more products are going to be present at equilibrium. If you have a pretty small K value, then there's going to be more reactants present at equilibrium. So if K is greater than 10, your equilibrium is mostly products. If it's less than 0.1, it's mostly reactants. And if it's about 1, then your equilibrium lies right in the middle. Now, we're not going to have to actually calculate values, but you do need to know how to interpret values that you're given. Le Chatelier's principle tells us that when a system at equilibrium undergoes some kind of stress, the equilibrium is going to shift to reduce that stress. These stresses are pressure, concentration, and temperature. If the pressure on a system is increased, the shift is going to go towards the side with fewer moles. Okay, now the value of KEQ is not going to change with a pressure stress. Okay, so if the pressure is increased, your equilibrium will shift towards the side that has fewer moles. So for example, let me move that. If we increase the pressure in this system, we start with 14 gas molecules, 2 ammonia, 5 nitrogen, 7 hydrogen. We increase the pressure by maybe decreasing the volume, then that means that our equilibrium is going to shift toward the products because there's only 2 moles of products that are produced per 4 moles of reactants. All right, so we end up with 6 ammonia, 3 nitrogen, and 1 hydrogen. So we're going to produce more ammonia to accommodate that increasing pressure. Decreasing pressure, you're going to shift towards the side with more moles. Now remember, we're looking at coefficients when we talk about moles. So if we decrease our pressure, then our shift is going to go towards our reactant side because there are more moles present here. Okay, we have 1 plus 3 is 4. So when we decrease the pressure, we're going to shift toward the reactants. If we increase the concentration, you're going to shift toward the direction that will reduce the concentration of that species. So for example, if we add more ammonia to the system, here's our ammonia. If we add more ammonia to the system, then that means more N2 and H2 are going to form. So our shift is going to go towards the left. So we're no longer at equilibrium by adding our 5 moles of NH3. So the equilibrium gets shifted to the left. If we decrease the concentration, the equilibrium is going to shift in the direction that will increase the concentration of that species. So if we decrease our ammonia, all right, we take away ammonia, we're going to shift toward the ammonia because you'll have more nitrogen and hydrogen that'll be reacting to produce that ammonia. Now, temperature is the only stress that changes your equilibrium constant value. If you take away heat, it shifts the equilibrium in the direction that produces heat. So if you have, this is an exothermic forward reaction, so if you cool it down, you're going to make it shift toward the heat. If you increase the heat, you're going to make it shift away from the heat.